The space industry has always been known for the huge amount of money that has to be invested to carry out a mission. Nevertheless, Cubesats have demonstrated that, in fact, it is possible to explore the universe at much lower cost by using commercial off-the-shelf products. Right now, we might be starting a new era of space exploration in which universities, small companies, and obviously well-known space agencies have the possibility of sending experiments to space. And that's why we are here. We are Cubesat Chefs, and we'll be facing a new challenge, a lunar flyby with a Cubesat. Without further ado, let's show you our proposal. This problem was proposed by one of our clients who gave us some top-level requirements which we need to fulfill so that our proposal is valid. We have listed all of them here so that the interested viewer can see how it will be the problem which we will be facing. Even though the design process is iterative, the first thing that we did was a mission analysis. In this mission analysis, we compared the performance of both chemical propulsion and electric propulsion. In this slide, I'm showing you how is the performance of chemical propulsion and what were the assumptions that we made. The most important one was that the burn would have to be symmetric at the perigee, so that only the radius of the apogee would be increased until reaching the moon's orbit. In addition, we have added an analysis that we did on how it affects increasing the burning time. As you can see, the longer it is the burning time at the perigee, obviously remember that it has to be symmetric, the lower will be the time of flight, but the higher will be the fuel consumption. When it comes to the electric propulsion approach, the trajectory obtained is quite different. As the viewer can see, it has the shape of a spiral, which is obtained when assuming a constant thrust along the direction of the instantaneous velocity. This table summarizes the results for each propulsion type. In addition, we have included the two thrusters considered, the 1 Newton high-performance green propellant and the miniature ion xenon thruster. It is clear to see that electric propulsion leads to much longer time of flight, but a remarkable decrease in fuel consumption as a consequence of a much higher specific impulse. In the end, we decided to go for lower fuel consumption since it would help the team with the goal of reducing the Cubesat size, and obviously the total mass. Moreover, the selected thruster has low power consumption with respect to other ion thrusters and a relatively high efficiency. Nevertheless, it is true that there are some drawbacks. For instance, the Mixie thruster is still under development, which means that the lifetime is not known. In the picture on the left, one can see the location of the thruster inside of the Cubesat, together with its 1 cm spherical tank, the mounting system, and the feed system. It is important to highlight that we consider a very big margin of propellant, since we tried to do further flyby maneuvers, as it will be explained later on. And another interesting fact is that for the sake of accuracy, we added a gimbal to control the thrusting direction. This will be of great help for the AOCS and the reaction control system.
After the moon targeting phase, we have a flyby phase in which we are required to have a maximum altitude of 100 km and having an orbit as polar as possible. For that, we designed a biplane targeting in which our maximum altitude was 90 km and we imposed an inclination of 90 degrees. The main objective of the lunar flyby is to collect science data. In order to do so, we have to point all the time towards the moon surface. We have computed the angular velocity and acceleration required to do so, and this will be an input for the AOCS subsystem. The most critical action after the lunar phase is transmitting all the science data to Earth. To do so, it is required to know the orbit in which we are left after the flyby. In addition to this, we have computed the required delta V for a second moon encounter. It has been checked that the fuel reserves allow to provide the required delta V and further expand the duration of the mission if needed. Regarding the AOCS subsystem, the following modes have been considered: the tumbling mode to stop rotation after the spacecraft detaches from the launcher, safe mode, slew mode, orbit control mode, which is in charge of having the thrust aligned with the velocity direction during the powered flight phase, science mode to acquire the data during the flyby, standby mode, and communication mode. The critical cases that were considered to size and choose the different devices composing this subsystem are science mode pointing, the action of environmental disturbance torques, the spin performance, thrust misalignment, slew time, and reaction wheel desaturation with RCS. It was chosen to include a commercial off-the-shelf ADCS system which already integrates sensors and actuators in the same device. It is worth noticing that this system has a maximum pointing error below 0.011 degrees, which is far below the maximum allowable error of 0.5 degrees. For the reaction control system, we have selected to use ion electrospray thrusters. It has the advantage of being more compact and much more efficient than the traditional cold gas thrusters. Despite these advantages, it has the drawback of consuming power and providing a very low thrust. Thanks to the selection of the places in which the thrusters were installed, we are able to provide pure torques around the center of mass or provide a net thrust without torque for small correction maneuvers.
The first step is to compute the power budget. To do so, we have considered the different configurations during the spacecraft mission, and we have seen that the most critical one for the sizing would be the orbit control mode. Moving to the solar array sizing, the main considerations that we have found are the following. First of all, we have checked that the most suitable solar panels that we need are the gas ones that have a degradation around 3% during a year, and we consider a time of the mission more or less of 5 years to compute that degradation. In addition, we have also considered a point in deviation at maximum of 30% regarding the normal with respect to the Sun. And the computation shows that the total panels that we need are 34 panels. In addition, regarding the battery sizing, we have considered the overall power that is necessary during the eclipse, and we also consider that the battery would have an efficiency around the 80% and a date of discharge around the 80% as well. And finally, we found a mass required around the 60 grams. Nonetheless, the battery that we have chosen is around 240 grams to be conservative. To analyze the data handling, we need to use the link equation to compute the necessary power that we need to provide to our antenna. To do so, we have done several assumptions as the ones I'm going to mention. First of all, the BPSK codification has been selected, and also the S band for communications. And to compute this power, we need to vary the distance from the different orbit and also the elevation regarding the ground stations. Finally, we have also computed the time access as a half a day. As we can see in the plot, the results that we got are that the maximum elevation that we found is around 70.5 degrees, and therefore the maximum power that we need to provide is 1 watt for our selected S-patch antenna that ensures full coverage during the whole mission. The next step is to size the structure that will contain all the components.
The main purpose of the structure is to keep all the elements protected and attached in the most compact manner possible. For this, we were able to reach a 6-unit Cubesat, so that we achieved our purpose of reducing the size of the Cubesat. Also, the structure needs to withstand the loads that will appear especially during takeoff. So for that, four bars were located in the 4 corners of the Cubesat, and these were analyzed for the usual accelerations of the Soyuz, which are 5G and 1 in longitudinal direction and 1.8 in the lateral direction. And also 2 panels were added to separate the subsystems and also to isolate, especially for the propulsion subsystem, since this will generate a lot of temperature and we do not want our electronic devices to be affected by this.
The deployment of the solar arrays is performed after the DSP maneuver. This is done by releasing the elastic constraints that kept the solar panels folded. As we can see in the video, this will be done longitudinally, one by one. And furthermore, the solar panels are equipped with a electric motor that allow them to rotate to facilitate the orientation towards the sun. Then the RCS controlling the z-axis of the Cubesat is pushed away from the structure and then locked by a non-return mechanism that will keep this system located, as we can see in the video, outside of the structure. This will increase the moment that this produces, improving the performance. Now that all sub-elements are properly distributed along the structure and we know the location of all of them, we can perform a thermal analysis of the Cubesat.
The job of the thermal engineering is to monitor and control the temperature of each component of the spacecraft throughout the entire mission, so that at every point of the mission, the temperature of each component lies inside the operating range. Here I listed some of the operating range for each major component of the spacecraft. What we have decided to simulate the temperature evolution of each component is to discretize the spacecraft into isothermal nodes. So for every major component of the spacecraft, we have created a node. This node gets heated or cooled due to different contributions. We have external contributions due to the solar irradiance, the solar albedo, or the planetary radiation, for instance. We have some internal contributions due to the heat that a given component generates inside of its equipment. Then we have radiation. Either a component radiates heat toward the free space or internally to some other component, or they transmit heat via conduction. At the end, we arrive to this differential equation for each node. So this is a table showing the changes that we have applied in order to control the temperature of each component. Basically, the most important thing that we have done is to change the optical properties of the components of the spacecraft, allowing us to control easily the temperature evolution for each individual component. Also, we have included some insulators in some of the components that generate excess of heat, for example, the thruster, and we have included the radiator that is connected, for instance, to the payload, so it can radiate away the excess of heat. So this is the final model representing the different nodes in which we have discretized the spacecraft. We can differentiate some external nodes that radiate heat away towards the free space, and some internal nodes that radiate between them. What we have seen in some relative cases is that some components experience from overheating, so we need a way to get rid of that heat. So what we have done is to include a radiator, which is basically a surface in the structure with some different optical properties capable of radiate the excess of heat. So this is a simulation showing the evolution of the temperature of each component for a typical GTO orbit. This is one of the examples, but we can see here that if we don't apply any change to the structure, we don't include the radiator, we don't change the optical properties of the spacecraft, we don't add insulators, the temperature of each component rises to some point where it's unacceptable due to its operating temperature range. So we need to apply some changes in order to bound the upper limits of the temperature. What we can see here is the same simulation as before, but now with the changes applied to the spacecraft. We are able to observe that the temperature of each component is bounded between its operational limit, so the spacecraft is good to go for the thermal analysis.
This table shows the risk analysis carried out for the same process. As you can see, it explains which risks were accepted and which ones were not according to their criticality level, which goes from 1 to 10, being 10 the worst case. In addition, it gives some mitigation strategies and also further comments if needed. As a summary, we could say that in general, the most critical risks were the ones which could jeopardize the science mission, such as, for instance, high perturbations during the flyby, which could increase the periselenium too much, low point inaccuracy, or failure in the solar panels deployment. We will leave here a summary of the preliminary design process. Thank you for joining us in this space mission adventure. It has been a very fun experience in which all the components of the team have learned a lot. For further information on any aspect, please refer to the reports submitted. If anything is left unclear, do not hesitate to contact me.